New recording. All right, zoom in on this. Okay, hello again, everyone. So I will quickly go over these image-related material, and the final set of slides are about human visual perception. And the important thing here that we'll talk about is that the color space that we use, the RGB, and images are discrete. They have a certain number of pixels we discretize, and as I said, the pixel, since it covers a certain area, we usually use the center of the pixel to indicate its coordinate. For example, if we are going to shoot rays in ray tracing, we will shoot rays from the focal point, which is a single point, towards these pixels, and when we do that, we will shoot the ray that passed through the center of the pixel. Not all uh, pixels may be square. In different applications, we may have rectangular pixels as well. And the way we store these RGB values, either in most of the cases, we store both red, green, blue values per pixel. This is how we are going to do that in our PPM images. Um, and this cube shows the RGB color space. How this is 25500. They have pure red, pure blue, and pure green, and a combination of red and green gives you yellow, cyan here, and purple, or it may have another fancy name like the cyan or turquoise. Okay, uh, so we can also store these different colors. Either if we store all of them RGB per pixel together, it's called interleaved. We may also store them separately as if they're separate grayscale images. The blue channel only that contains a single byte blue values, the whole image, and another the green channel contains like grayscale, like 0 to 255 colors, which will indicate the green channel or the red channels. If we store the images like this is called planar storing, and this is called interleaved storing in an image file. Uh, we will have some virtual world scene description file, our computer graphics program, which will do the rendering. And the rendered image, we have an option to visualize show the rendered image either directly on display. So if your program have access to the monitor's frame buffer directly without writing to a file on disk, it can directly show it on the monitor. Okay, this is what many all of the games that we play, for example, they are like that. They do not actually store those images at all on the disk. The images are displayed on the monitor by accessing the graphics card's frame buffer directly. Usually, in order for the monitor to talk with the graphics card, there are drivers, and these drivers basically sometimes they have a designated memory. Most graphics cards these days, they come with some designated frame buffer memory themselves. So the color values that we write are in a place called frame buffer in the memory of the graphics card, and that frame buffer should be sent very fast to the monitor or the monitor's driver, whatever monitor you have, display device. It reads that frame buffer memory of the graphics card directly in a very fast manner, so that we do not have any delays when we change the frame buffer's pixel value, pixel color value on the frame buffer. It should be immediately visible on the display device as well. These are all about writing drivers to your display devices, writing drivers to your graphics cards. It's about really writing code that is very close to the hardware. And sometimes in our first part of the course, when we talk about ray tracing, we will output we will output our images to store them on the disk as an output image file, because we don't want to deal with how to directly write to frame buffer. We need to have some libraries to do that. Also, when we talk in the second part of the course, when we code in OpenGL, also OpenGL does not provide anything about the drawing directly on the frame buffer. Actually, OpenGL is a graphics library, but this getting a graphics context from the frame buffer is usually done by APIs that are close to the operating system. You need to have either use an additional library like glut or glue or sorry, there's glfw library, there is qt that, or Windows API. You can use Visual C, C++, or something else if you're programming in OS, for example. What I mean is that for a program, for a C program, to get a window on the operating system to be able to write some images onto that window, it's we need some libraries to do that. So in the first part of the course, we're not going to we're not going to go into these details, getting a graphics context and directly writing onto that. Instead, we will keep it as simple as possible with just pure C or C++ with no additional libraries. We will be writing a very simple output image file with the PPM format, and we will be able to see with a camera. We will have an eye to our virtual world. Yeah, this is the PPM format. This is the simplest one. Here is a 4x4 PPM image. It has a magic key at the beginning, P3, I think, saying that it's an ASCII PPM format. So it looks for this, and this dash simple PPM is the name of the file, I think, which is optional. But it's followed by the resolution of the image. It's a 4x4 image, so only 16 pixels, not 16 megapixels, just 16 pixels. So it's a just 16 pixel image. And as you can see, this 255 shows the largest pixel value we are going to have, largest intensity value. It's also indicated in this file. And every pixel, so 128, 128, 128. So the top left pixel has a middle gray value. And actually, the first 3 pixels on the top row are middle gray. Then we have red, green, blue. So red and some purple. A purple on the top right. Another gray, red, blue. So as mostly the image is mostly gray. I have some red, blue, and some purple here. Oh, and there is also cyan, green, and blue at one place. So if you view this image, right, actually we should have this image someplace. Yeah, it's this one. The image that we have 4x4 image, the PPM one, is the one on the left. As you can see, this is the midway between red and blue. This is the midway between green and blue. This is pure red, pure blue, and mostly the image is gray. So this is your 4x4 image that you will represent it in PPM. It's a very simple format, and tools like ImageMagick will be able to convert PPM to JPEG or PNG, whatever you want. And as you can see, when you save it as a JPEG file, if you convert it to a JPEG file, like a 4x4 window seems to be averaged here. For example, these 4 pixels become influenced by the cyan pixel, and it's a combination of gray and cyan values. This part is like purplish, this part is also like purplish. So this JPEG compression is very lossy in this 4x4 image, but when you have it on larger images, for example, this is also a JPEG compressed image on the right hand side. Let me have on the right hand side, this is a JPEG image with different quality settings. Quality settings basically determine the area that you average probably, and when you average over a larger area, you get more blur. So the image is more blurry when in a low quality setting, less number of colors are used. But with certain JPEG compression, you can still get really high quality images if you look at from a distance. If you still, I mean, if you zoom into them, you will still see these. I mean, if you zoom into these images this close, when you see the individual pixels this size, you will probably notice the differences between lossy and lossless compression. Okay, but yeah, image PPM is a very simple image format, but yeah, it's a very inefficient due to lack of compression. Also due to the ASCII PPM there is also binary portable pixel map in which we store only 1 byte per color channel. If you have it in ASCII, we may spend like 3 bytes per color channel because of the 3 digits. But actually, these are just every value that is stored in red, green, blue is just 1 byte of information. So actually, if a binary PPM would save some space, but still an 18 megapixel image, 18 million pixels. This is what it means. If even in binary PPM, we would need 3 bytes per pixel, which means that this will be close to 60 megabytes of image. So 18 times 3, 54. So 54 megabytes will be required for an 18 megapixel PPM image, binary image. If it's ASCII, I think this is the how we would compute it in. This is an ASCII. So this on the left-hand side shows 18 million. So this is 18 megapixels. Okay, and we have 3 channels RGB. And this 3.57, where does this come from? I think it's the average number of digits per pixel, average number of bytes per color channel, including the spaces. Okay, and this is dividing it back to, if you're going to write it in megabytes, this is the number of bytes that it will occupy, this many bytes. If you multiply it with a million, close to a million, you get the megabytes. It would take around 200 megabytes if you store it in ASCII. If you store it in binary, you will just get rid of this 3.5 multiplication and it will be close to something 60 megabytes. Yeah, the 357 comes from this. We have 10 single character numbers from 0 to 9, the intensity values, 90 from 10 to 99, 2 bytes, and 156 3 bytes, and add 1 to that. This 1 comes from space delimiter between the values and or the end of line character, and it gets you an average number of 3.57 bytes. Yeah, if we use the binary PPM, it will be 54 megabytes for a 18 megapixel image, but still it's still too much. 54 megabytes. Therefore, we have compression techniques. We use JPEG, PNG. PNG is a lossless format, but it still compresses image, because an image, since, for example, in an image, when you have lots of gray values in an area, you don't need to write all those gray values separately. You can have some kind of a run length encoder to say, I have 20 or 100 gray values in this region. I mean, there are compression techniques that are widely known, and you can use that to compress your image so that they will be stored more efficiently. Lossy compression, an example is JPEG format. It makes a much more efficient storage, but it loses at the cost of losing some detail. But JPEG is a nice format that this loss is not perceived by the human eye that much. So it actually takes into human perception into account when it does this averaging. Okay, so how do we capture the image? We defined our color range as this. The light intensity, sometimes called luminance, in the world is actually not restricted to such a set. So here, the next set of the slides is actually talking about, can we, with just those 1 byte from 0 to 255, can we represent the brightest reds or the darkest black? For example, if you have really black color on your monitor, is it really black? Or does it have, I mean, is it dark gray? or can you get pure black, or can you get very bright like the sunlight? Can you unfortunately in real life the color range is a lot more than this, between 0 and 255. The actual color range is really wide, and therefore when we are taking photos with your camera, uh, we actually sometimes make sacrifices depending on the exposure time. If you, for example, you must have seen this. For example, if there is a very bright part of a photograph, in order to represent detail in that bright part, the other parts are going to appear dark. But if you want this dark parts to perceive detail in these dark parts, then you make the exposure longer exposure, but this time the bright parts are going to saturate. There will be no detail in that part. This brings us to the concept of high dynamic range images, which you may be familiar from your phones, HDR mode. HDR stands for high dynamic range images. What it does is there are different techniques. It based on the scene, it looks at a scene, a certain luminance field, and maybe remap this 0 to 255 values based on the lowest luminance and highest luminance in your scene. And if it's not enough, for example, sometimes it takes multiple pictures and combines them together. Different parts can be combined together to represent these. But you may ask, we are still limited by our display devices intensity range, right? I mean, if your display device cannot show that as bright enough, I mean, whatever, at the end, we will be storing all these photographs as images with RGB values from 0 to 255. So that's a big limit. But there are display devices, or there are image formats, or high dynamic range image formats, which actually try to capture these larger width of luminance values. So yeah, this was the example I was talking about. In a low exposure image, the dark parts are really like dark, but the clouds, you can see the bright parts, the clouds are really detailed. But if you want these dark parts to view, if you increase exposure, this time this part saturates and it becomes all white, because the amount of photons that you capture in your sensor, it increases. So if you open your lens long enough, lots of light is going to come to there, and that sensor is going to saturate with photons, and it's just going to display the brightest white it can display, and there will be no difference between different cloud formations in order to see this part. So, but what we could do is we could combine these two images somehow. For example, maybe these dark parts, you can use this part of the image, this light part, you can just use the second image to do that. And you can also, another thing is this dynamic range, the minimum intensity here and the maximum intensity here. You can do a remapping of those color values between this max and minimum range. But again, this course is not about high dynamic range imaging. There is a course offered by Ozoja on high dynamic range imaging. If you're interested in this, you can take his course on this subject. But just know that with in real life photography, for example, the range from 0 to 255 is not used, is not sufficient to represent the real range. In astronomy, I think they're also using things that are not in the visible range. So they use lots of the radiation in astronomy. Usually when they try to visualize things, they map to something human eye can see so that we see them as images. But the actual signals, the actual signals that, oh, let me close the door. There's some noise coming in. I'll coming in a minute. Okay, so in astronomy, I think the signals that are captured by those telescopes are not limited to just visible light, and therefore, in order to see some images of distant stars, they map to something. The images that we see, they're just artificial images. All right, they are not real view. Most of them are artificial images. They just map them to certain colors, so that they look like nice images. But again, this can be used in astronomy. The range of the signals, the radiation that are received by those telescopes, some of them may be very low for very distant stars. Some of them may be very bright, and therefore they may be using these techniques in astronomy as well. And cameras, they control their exposure to decide on proper range. I mean, if you're taking a picture with your camera, remember when you press on certain points, it will make the exposure so that pointed place is going to appear nice. So you can actually sometimes exposure is automatic. Sometimes you can have the exposure to have some part of your scene viewed as nice as possible. Sometimes with professional cameras, you can manually adjust the exposure. So this is and when we do quantization, when we quantize this from 0 to 255 pixel value mapping, things become like this zigzag. And why does this matter for computer graphics? In computer graphics, we generate images just like camera captures, and our artificial scene may have luminance values not limited. For example, you may want to have some bright sun in your computer game, and how do you represent that? And that's we have to mimic what the real camera does. So sometimes we may need to borrow techniques from image processing or imaging to get in computer and apply them in computer graphics applications as well. So we can here is the HDR image capture process, different exposure levels. So 1/1000 seconds, very quick, so low exposure. And if you increase the exposure to 1/30 seconds, you get this very bright image. Sometimes you can combine all these things to get a high dynamic range images. And there are displays that can display high dynamic range images directly, but our regular displays are not capable of displaying all of them in this high dynamic range. So what we do is we usually map. The tone mapping is used to map different values in this range to a low dynamic. So this LDR means low dynamic range, which is our regular displays, and they can be done like this. But as I said, in our focus is not on this in this computer graphics course. So I'm going to skip these parts. If you're interested in, there's more detail on this website. And then after we generate those images, we either send them to the graphics card and the monitor, the video card, which is the monitor's driver. And there are different display devices. There are ranging from smartphones to larger displays, even billboards. You may have very large billboards as display devices. You may have dome displays, which are spherical. Not all of them are rectangular like this. You need to take into account all these effects. These days, for example, virtual reality headsets, they use usually rectangular displays in virtual reality headsets, but maybe a spherical displays in virtual reality headsets will be better to have a higher field of view in a virtual reality headset. And the last thing I'm going to talk about in this set of slides is that these signals, RGB signals, as I said, are not linear. The output luminance, when you change the image pixel value from 0 to 255, the final brightness, so luminance is like brightness, the brightness value you see, you perceive, is not going to be linear. If it was linear, it would appear like this. I mean, not like this. I wasn't able to draw a straight line, but if you imagine that this is a straight line, if it was linear, it would be like this. But it's more like a non-linear relationship between voltage values or the image pixel values and the luminance. And therefore, display devices has something called gamma correction. You may have heard this term before in your monitor settings. You can, or your display driver settings. You can play with this, the gamma value in your monitor, and see how it changes this nonlinear relationship between pixel values and and the actual luminance that you perceive. The gamma value is the exponent that is used to correct this nonlinearity. And here is the simplified display model. This is the luminance out. This is the voltage value that is applied, which comes from your image RGB values. It's multiplied with some constant. A constant is added to that. And here is the gamma. The actual RGB value is we take its exponent to model this non-linearity. Yeah, the goal is to make the graph linear because you want the RGB values from 0 to 255, as I said, to have a linear relationship. And I have 128 as the red, green, blue value. I want to have the medium gray because it's easier to design your computer graphics application with the linear relationship in mind. So the goal is to linearize the nonlinear relationship between voltage values and luminance values. So this is brightness, contrast. These constants actually mean something. They refer to brightness and contrast. And here, this is the measure. This is the ideal one. Here are the pixel values in some monitor, and the gamma value is 2.2. When we perform the gamma correction, the input signal is raised to the power of 1 over gamma before being stored. This allows the luminance received by a camera to be linearly proportional to the luminance emitted by the display device. All right, so again, the answer to your question is yes. The goal is to make these two things, luminance and voltage, linearly proportional to each other. So here are some gamma correction results. Look at this one. This is the gamma correction. If you don't do any gamma correction at all, the image looks like this. After gamma correction with the linear relationship between luminance and RGB values, the image looks like this. If you overcorrect, if you overshoot this gamma value, you may have things images that look like saturated. This is the ideal. In ideal case, we want to have a linear relationship. Usually this gamma correction is applied in the last step, and we will not deal with gamma correction in most of the applications we deal with in this course. It's done automatically by the monitor in most of the case. Without gamma correction, sometimes you may have dark images. Usually the gamma correction is applied in the last step of a computer graphics application. All right, so that's it for these sets of slides. And the final thing I'm going to talk about is human visual perception, human visual system. Oh yeah, so in Photoshop also you can have this gamma correction thing. And I teach about this gamma correction myself, but I don't use it that much, so I didn't digest the concept myself that much. All right, so that's something that I want to say. I'm not into images or this gamma correction is already handled by the monitor, so I'm more interested in the rendering algorithms, so that's why I'm skipping those parts quickly. But if you have any trouble, since I didn't digest them myself better, so I cannot teach them very well. If you didn't understand what gamma correction is, please read the text, okay? Read the book to understand it better. Or maybe follow Ozoja's lecture in this part, in gamma correction part. He may teach this part much better than I do, because he deals with HDR imaging and applying these image techniques on the final rendered image. So he may teach this gamma correction part better than I do. Either read the book or, I mean, if you have trouble in understanding what gamma correction is about. Okay, now human visual perception. These are the last set of slides that I'm going to talk about. There are only a few of them. So we may finish early today, and next week on Monday we will start our first algorithm, ray tracing, which is I hope going to be very fun. I will be writing some code as I teach ray tracing. There will be lots of mathematics involved, but the mathematics really is going to be very simple mathematics, like parametric line equations, finding the coordinates of pixels given the lower left corner of the frame window and things like that. Not complicated mathematics at all, just regular multiplication, addition, and then some simple linear algebra. Okay, but then when we talk about some intersection tests, we are going to talk about how do we intersect a three-dimensional line with a three-dimensional triangle, or how do we intersect a three-dimensional line with a sphere. We are going to think about things like that, and it's going to be fun, as I said. Not very complicated mathematics, but after we write the code, the result will be really nice. It will be nice-looking images that we will be generating. Okay, the human visual system consists of the eyes. So here is the top view of the human visual system. So we are looking, or maybe bottom, but it's just a slice. Either you're looking at this from the top or the bottom, depending on how you perceive it. I think it's the top view seems to be a better way to look at this. So here are our eyes. Lights come from this direction. So light rays are coming to our eye this direction, and they are received by the retina. Okay, the light rays. There are cells here which are connected to some neurons. I mean, there are neuron cells that receive these photons. They are excited by these photons, and these pathways, these neurons connect to the brain, and then we perceive it as some shape. Okay, but the entire visual system, I mean, how we perceive, for example, there's perception. I mean, we see the light rays is coming all part of the retina, but sometimes lots of cognitive things happen in the brain as well. You may be looking at things but not being aware of something that exists there. So selective perception. There's selective perception that happens, and actually illusionists, they use this a lot to perform tricks. Okay, illusion tricks. People do, although we receive the signal, we may not perceive the signal with our brain. So you may do some magic tricks by making use of the human perception differences. So the eyes works like this. There is the cornea, iris, the lens, and here is the retina. Okay, so this part is the retina, and there's some part of the retina in which there are no rods or cones. So that's like our blind spot. We have a blind spot in which no photons are collected. And here's the optic nerve that is connected to the brain. I'm not going to go into too much detail, but as you can see, it's not rectangular. It's like there's some curvature in our retina. And there are different types of cells in our retina. And what happens is that if we have a tree here, light rays coming from different parts of the tree enter our eye, and it forms an image in the retina. And as you can see, the image is going to be formed reversed. The top of the part, for example, the leaves that are at the top of this tree are going to appear here. The light ray comes here, and the light rays coming from the bottom of the tree are here. So the image that is formed in the retina is actually upside down. And this is corrected by our brain automatically so that we don't see trees upside down. But in our eye model, we don't want to have images that are upside down. We are going to do something really interesting, which doesn't happen in real life. Since we are really free in terms of our computer graphics application, we are free to have put the lens or the image in any place we want. This is the model that we will be using. the image is going to be formed in front of the lens. So if this is like the lens, or this is like the eye, just imagine the retina that is actually in front. So the whole thing is the eye. Okay, let's assume the whole thing is the eye, and the light rays come through a distant point. For example, there's a tree here. Okay, the light rays are coming, and this is the focal point. The focal point here in the eye, as you can see, is the lens, just behind the lens. That's the focal point. And the image is formed behind the focal point. But if we have our retina or our image plane in front of the focal point, the tree is not going to appear upside down. The tree is going to appear same straight up as in the real life. So this is going to be the eye model or camera model that we're going to apply. There will be some focal point behind the image plane, and the light rays will be coming towards through the image plane to this focal point like this. And this will be our field of view. We are going to be able to see things that are in this cone. It will be three-dimensional. We are going to see this will determine the size of the image that is in front of us. This frame window, the image window, is going to determine our focal field of view angle. All right, so we are going to talk more about this when we talk about ray tracing. But this is the rays coming like this and merging at a focal point provides what we call perspective vision. Okay, with this rays just converging to a single focal point, far away objects are going to be projected into smaller regions on this image plane, and close by objects of the same size. You can have the same size tree. If you move the tree closer to the eye model, as you can see, it will occupy more space in the image. They will appear larger. Okay, so that's one model. Another model could be, why do we have light rays converging at a focal point? Because that's like that's closer to human vision, because we have perspective vision. But for certain applications, for example, maybe for architects, industrial designers, this perspective, seeing things in perspective, may not be desired. For example, imagine you're viewing a cube on your screen. Although it's a cube, if based on perspective, it will appear like not a cube, like something distorted like this, because far away side of the cube is going to appear smaller than the closer side of the cube. So it will not look like a cube with this perspective. And if you're an industrial designer or an architect, you want to see the distances on your screen as they are in real life, you may not want perspective vision. For that, we can actually solve this problem by shooting the rays parallel to each other through the image window. They do not converge at a focal point. They do not converge at all. They are parallel to each other, and they are orthogonal to the image window like this. Therefore, such a vision is called orthographic vision. Okay, that's called orthographic. I'm writing it in the chat box, orthographic. And since we write our own computer graphics applications, we are free to have non-realistic visions like these, orthographic view. Okay, and with orthographic view, things will appear the same size as they are, whether they are their distance to the image plane will not matter at all. Okay, I read a short story like 2-3 years ago. There was a really nice short story. This science fiction writer made use of combined orthographic and perspective vision to tell a really strange story in which there is an island where close to some country, and the people in this country are afraid by the giant that lives on the island. All right, so there's a giant human being living on the island, so they're afraid and they don't want to go to that island. But some brave people go to the island, and as they start closer to the island, they see that the giant figure is shrinking in size. So when they get close to that person, they see that's actually the same size as a regular human being. So why does it appear as a giant? Actually, it's not a giant at all. That person has some deficient defect called orthographic visibility. So that person that is living on the island is visible to everyone in an orthographic manner. So even if he's very far away, he appears always the same size as a regular human being that is closer to you. So therefore, if when it's far away, you perceive that as a giant, because we are so used to perspective vision that you see that person in the island. And that's the interesting thing, is that that's a mixed perspective and orthographic. We don't have such visual vision systems in computer graphics application. But if you mix perspective and orthographic view, you may get these interesting stories. So yeah, the focal point, moving it backwards also makes the perspective seem zoom in. So we will see things like, for example, you may move. We will ask questions like, what happens if I move this image plane closer to the, without changing its size? If I move it closer to the focal point, what happens? Our field of view enlarges. We are seeing larger places. The effect is like zooming out. And if you move if you move this image plane closer, farther away from the focal point, what happens is that the field of view gets smaller, but the tree is going to occupy more space on the image relatively this time. So in order to zoom in to a certain location, what you do is, therefore we have these telescopic lenses, right? Telescopic lenses allow you to move it's not the image plane that is moved further, but if you make the distance between the focal point and the image long enough, your field of view shrinks. You're only focusing on a certain part of the scene, but that part you can see larger. So zooming in has this effect. So by playing either with the focal point, moving it backwards or forwards, or you can think of relatively moving the image plane forwards or backwards, you can have this zoom in, zooming in, or zooming out effect. Yeah. Yeah, that's right. In orthographic vision, the focal point is at an infinite, as an infinity, infinite distance away from the image plane. Exactly. So yeah, there are two cell types in our retina: rods and cones. While being more numerous than cones, rods do not exist in the fovea, and there is only one single types of rods. Our night vision is not sharp and colorful. Rods are active under low light conditions, so we have more rods at our peripherals. At the center, we have more cones. So you may try this interesting experiment that maybe you may have noticed this as well. In a very low light condition, imagine you're in a room and the luminance, the intensity of the light is very low. You have some object. You don't see the object when it's in front of you. Okay, if you directly look at the object, the light is so low that you don't see it. But if you move the object towards your peripheral, the object becomes visible. Okay, so sometimes when you see an object at your peripheral, it may be visible, but if you directly look at it, it may not be visible in a low light condition. You may try this experiment yourself. It means that at our periphery, we have things that can see better at low light conditions. This may have been evolved as a defense mechanism. For example, if an attack comes, usually attacks or things that come, if something is in front, you already have your attention on it. But you have to, the parts that you're not paying attention, the peripheral of our vision, we need to be more alert in those parts. Therefore, maybe in evolution, we have these parts, the roads, becoming more abundant on the peripherals, maybe due to this. Yeah, cones are very dense in the fovea, and we have a blind spot. And here's how the wavelength. We have blue cone cells, green, red. So actually, this red, green, blue is not very artificial actually. In our biology, in our cells, actually, cone cells also, there are three types: red cone, blue cone, and green cone, and they are capable of perceiving different wavelength lights, as you can see. But we are not going to talk about these things the remainder of the course, so I'm skipping these quickly. And there's also non-linearity. Just like the monitor's voltage being non-linear, the human response to light is also non-linear. For example, this is really dark. This is 100, 100, 100. This is 50, 50. We see a larger perceived step here than compared between these two gray values. Yeah, these are both like gray values, a little bit darker gray, lighter gray, but the difference between this pure black and this middle gray, this step is perceived larger than the step perceived between these two things. Although in terms of RGB values, and even if you have the gamma correction on your monitor, the distance between these two are 50 integer values. All right. So also in terms of perception, cognition, the way we perceive brightness is not linear. This is the brightness curve. Visual perception allows for different various optimizations in computer graphics. If you're interested, then you may look at these papers and how cognitive science perception helps computer graphics applications to have better effects. So in summary, we render the frames in discretized images, and those images are sent to displays which produce a light field, and this light field is perceived by our eye. We see images that are shown on our screen. We sense, with our brains, we sense shapes, geometry, material types, we sense motion if we are moving images, and then we make use of, we interpret these as semantics. Football players playing something, you follow the ball, we perceive that, oh, okay, there's some goal scored there. So these things, giving meaning to what we see, happens basically in the brain. All right, so that's it for the first week of slides. Starting from next week, we will start our first algorithm on rendering, which is the ray tracing algorithm. It's very simple. The basic version of ray tracing is very simple, and we are going to be able to generate very nice looking images of virtual worlds, okay, with ray tracing. All right, so that's it for this week. I'm going to post the links to the recorded videos on AutoClass and Onco, so you will be able to watch them later if you want. Any questions before I finish today's lecture? All right, no questions. Seems like nobody has any questions. So see you on Monday, and we will start ray tracing on Monday. Oh, the book should be available in the bookstore. We had enough copies in the bookstore, but if you want to buy a hard copy of the book, you can check the bookstore. If it's not, please, or if you want the PDF of the book, you can send me an email, or we may also share the PDF with the class if you want. I will talk to Ozace about this. But yeah, in the last Monday lecture, the reference book, Hearn and Baker's Computer Graphics with OpenGL book, a friend of yours has actually shared Drive link to the PDF of that book. If you're interested in also in the course textbook, Shirley's course textbook, again, we may share a PDF of that with you. Okay, it's not in autoden.com TR, so we will make sure the bookstore has this book, or we will just send links to where you can purchase this book in Turkey. All right. Have a good day, everyone. Okay, thanks. See you on Monday at 11:40. Bye-bye. Thank you.